Okay, so this video is going to look at circle theorems and particularly making sure that you're able to know the circle theorems and then be able to apply them in order to solve angle problems within circles. So the first circle theorem that I'm going to go through is the triangle and semicircle theorem, where you can see in the image below that there's a triangle drawn inside a semicircle, where one of the points is on the circumference and the other 2 points are at either end of the diameter of the circle. Now, the image will animate a bit, and what I've done is use a program called Geogebra where I can move points around. So in a minute, you'll see that this point will move, and it doesn't matter where I move it along the circumference, it is still going to give me an angle of 90 degrees. And this is what's important about this circle theorem, in that it will always give you a 90-degree angle. And now, as I move the diameter about and leave the other point fixed, you can still see that it stays as 90 degrees. Now, your main thing you're going to need to do is just remember that that fact is true and then be able to use it. So just remember that the angle at the circumference is always 90 degrees for these triangles. The next circle theorem I'm going to look at is to do with the angle between a tangent and radius. Again, in the image, you'll be able to see that the angle that's been created is 90 degrees, and this will always be true. So again, by moving around these points where the radius here meets the tangent, as I move that point where they intersect around, you can see that it's always going to be 90 degrees. And so this brings about another theorem which you need to remember, and that is that the angle between a radius and its tangent is always going to be 90 degrees. Now the next circle theorem is about meeting tangents, where they meet outside of the circle. So we've got two tangents coming from points C and D on the circumference of the circle, and you can see that they are going to meet outside. So what I've done is using Geogebra is actually measure the distance, which you can see they're both staying the same no matter how I move the point. So whilst the rest of the program calculates everything else, that distance from E to C and E to D is remaining fixed. Now this is quite an important one because it also coincides with the 90-degree angle that's being created between the tangents and the radius. So what you're going to have here is a particular type of kite, and certain angle facts are going to come from here. So you want to be able to recognize when these two tangents are about that you're going to have this sort of fact going on, that they are the same length, and that you'll want to use that. Sometimes this can be used in a trigonometry problem which is buried inside a circle theorem problem, so it is something that you would need to look out for. The next circle theorem that you need to remember is that the angle at the center will always be double the angle which is at the edge. And so this is illustrated here. Now when I did animate this, I found that the rounding meant that the angles were not always going to work out that one was double the other. But you can see that they're from the same chord. Where we have D and E being a chord, that we've got one point on the circumference C and the other point is at the center A. And this is the traditional looking diagram that people see and will remember, but I'm going to illustrate that it actually can look a little bit different. So in this one, as it animates around in a minute, you'll see that that angle there is still saying it's 52, and then as I drop it to there, you can see that yes, it's still 52, but the image doesn't look like what you would normally see. And sometimes this will catch people out in questions. So recognizing that this little ribbon type diagram, or bow, you're actually going to still be using that same fact, even though it doesn't quite look like it. And so you just want to keep an eye out for that as it goes round, because that's going to be the case. Now as I move this point, the angles start changing. You'll see that the rounding doesn't always work out, but even as those angles are changing, you can see that one of them is still being double the other. Now in a minute, I move this point E all the way up to the top, and this is going to be a little bit of where you could use this as a proof. We'll just pause it there, where you can see that we have D, A, and E all in a line because of that 180 degrees, so it's a straight line, and the angle at C is 90 degrees. Now this goes back to the original circle theorem, the first one, where the angle at the edge was 90 degrees when it's inside a semicircle creating a triangle. And this is one way in which you can prove it if you can use this theorem to prove it. Now this goes into angle proof, which I'm not going to spend a lot of time on in this video, but it's something worth considering, particularly with the new GCSEs. Now the next circle theorem I'm going to go through is the cyclic quadrilateral, which whilst in this diagram it starts off looking like a square, which is just a nice way to start it, you'll notice that I've color coded the angles. Now what will happen as we animate this diagram is you'll start to see that although the angles do change, we pause it there, you can still see that the ones which are color coded will always add up to 180 degrees. Now this is the property of cyclic quadrilaterals that you mainly need to remember, that opposite angles will add up to make 180 degrees. And it doesn't matter what type of quadrilateral, it doesn't matter how I move this around, you can still see that the angles are going to add up to make 180. Rounding was not so much of an issue in this one. There have been questions where you might have to prove that this is true, and again that goes into that other area, but this video will mainly look at the idea of applying it. So bear that in mind, that you may need to prove it, but for now we're focusing on remembering these as facts. Now the next one that I'm going to go through is the alternate segment theorem, and this is a diagram which most people do forget, or they don't really see it very often in a question. And what you've got is a tangent and then this triangle which is drawn inside the circle, where one of the points is where the tangent meets the circle. So what you've got are two angles I've labelled up here which are exactly the same, and no matter how we move the points around they will still be the same. So the angle that's between the tangent and the chord CD is equal to the opposite angle, which is referred to as the alternate segment. And so this is the point that you would need to remember. So as we animate this diagram, as I start by moving this point, you will see that because it's from a chord it doesn't change, but over here as we start to move this point round, you can see that as those angles are changing, those two particular are staying the same. And this is the idea that you need to remember. A few people often get themselves into thoughts about lines being parallel here and start inventing that there are alternate angles rather than using alternate segment. So you want to watch out for that, particularly in these types of problems. Don't jump to a conclusion about any of the sides. Nothing is a given fact. So the final circle theorem that I'm going to go through is between a radius and a chord, where the radius is intersecting the chord at its midpoint, which is labelled E on the diagram. Now what will happen is that this will create a right angle. So there are various facts that are going to come up here, because you're going to be using the fact that it does bisect it, that you are getting a 90-degree angle, and so a range of questions can come from this. Now there haven't been many questions that I've seen using this particular circle theorem, so it is one to keep an eye out for as we go into the new GCSEs. Now as it animates and goes round, you'll see that it does illustrate that no matter how I move the points, we are going to get this 90-degree angle. And that would be the final fact to remember. Now the next thing I am going to do is I am going to go on to look at an exam style question where we're going to put some of our circle theorems into practice. It's quite rare to get a question where you'd have to put all the circle theorems into practice, so we're only going to be focusing on a few. So here is a question where all we're really going to have to do is apply our circle theorem facts to solve a problem. Now at the minute with this question I have not put the question in. I've given you the information that came with the question, because this information which is down here that I've highlighted is important. Make sure you read this, because you don't want to make any assumptions about the diagram and about any of the points and how they interact. The other reason I've left the question out is because it's actually not that important in my opinion to start with, because what you want to do is find any angle you can. Don't be fixed on the angle you want, because that can sometimes cause you to go down the wrong path and you may end up making assumptions. So you need to make sure that you avoid that. So the question I'm going to focus on is the second part of the question in this case, where it says work out the size of the angle ABC and give a reason for your answer. Now the reasons will be important, particularly in the new GCSEs where your marks are dependent on these reasons, particularly if it does say you must show your working or explain each stage of your working. You've got to make sure you're including keywords and terms. But if we just focused on angle ABC, we would be tempted just to try and work it out, given that we only know that 36 degrees, and we wouldn't work anything else out. And that could lead to a mistake. One mistake I've seen someone make is to say that ABC is 36 because it looks the same. and that's not what you're going for if you're trying to answer this type of question. So when answering this question, going through the information that I highlighted, one thing we know is that DA is a tangent, and so that means we are going to get a right angle down here for angle OAD. And this is the first stage that I went through to solving this problem. The next thing was to recognize that OAD was a triangle. And we know this because in the question it does tell us that DCO is a straight line. So we know that that's going to be true, which means we can get this angle up here, AOD, which is going to be 54 degrees. Now at this point, I'm not worked out or ABC, and I've had no guarantee that what I'm doing would get me ABC. But by doing this, I will have worked out many angles, and then I'll be able to get the one that I want. So because the angle I want is ABC, I then have to think about which circle theorem could I use to work that out. And the one we want to use is that the angle ABC is going to be half the size of AOC, because these are both angles which are from the same chord, one's on the edge and one's at the center. And so that means that ABC is 27 degrees. Now, when you are answering this in an exam, you'll want to put all your working out down properly. You'll also want to make sure that you're including the key terms so that you're explaining correctly everything you're doing. That way you can ensure that you do get the maximum amount of marks possible. If you aren't sure about how to answer a circle theorem question, start working out some of the things you can. You'll be surprised at some of the marks you can get just by actually working some things out, even if you don't necessarily get the answer at the end. Hopefully that video has been useful, so if you'd like to leave any feedback, please do so below. Thank you.